Hello, my name is Mikołaj. I'm a developer of the mlatom quantum chemistry package, and today I would like to show you a tutorial on how to analyze results of nonadiabatic molecular dynamics simulations using mlatom. So, the data used in this tutorial is available at the following link, following DOI, shown here, and it is taken from our paper on active learning for trajectory surface hopping simulation, which is available at the following link. In this paper, we have introduced a fast and efficient protocol for active learning of nonadiabatic molecular dynamics, and if you are interested in surface hopping methods in general, you should definitely check it out. I should also mention that this tutorial is in the form of a Jupyter notebook, which you can run online free of charge on the Zax cloud, or you can download it and run it locally on your machine. Obviously, as the first step, we need to load mlatom as a Python package, as shown here. And then our first example for today will be analyzing the hopping geometries in the dynamics of full vin. So, which has been, for example, done in this reference provided here. To do that, we will need to define a function for extracting the hopping geometries from an mlatom molecular trajectory object, which is provided here. And then we will load a full vin molecule in the mlatom format that is stored in the file ecmo.json, which then we can write as an XYZ file and view, as shown here. And we will need the XYZ file to check the numbering of the particular atoms, which I have done already. For our analysis, we will need to look at the 4 dihedral angles, so the 2 cis dihedral angles between these 4 atoms and these 4 atoms, as well as the 2 trans dihedral angles, this 4 atoms and those 4 atoms. We will also need to look at the bond length between the CH2 moiety and the central 5-membered ring, so this bond length, as well as the hop times from the dynamics. So here I define all the Python list for all these quantities that I will analyze. Next, I iterate over all the 50 trajectories that I have downloaded here, load each one of them, and then use the defined getHopGeometries function to obtain the hopping geometries. And finally, I look at each of these geometries and extract the relevant data. So the bond length, the dihedral angles, and the hop times. And this functionality, molecule.dihedral angles, is a new functionality added in this mlatom release. So I run this code. And after a few seconds, I should have the results. Now the next step will be calculating the mean dihedral angle, so the average of those 4 dihedral angles that I calculated here, according to, for example, using the formula provided in, for example, this reference right here. So we wait for this cell to finish executing. And now, once this is done, we can calculate the dihedral angles. Now we want to plot our results, and the most convenient way to do it is to use the matplotlib Python package, which I import here. And then I plot the results. So I use the plt.scatter function, providing a color map, and the color map I used, so I color the points with the hopping times. And we can obtain this nice publication quality and good looking and very informative plot. Now very easily using mlatom. And for a bigger plot of this kind with more hopping points, you can check out this reference provided here. And in this tutorial, I would like to also show you a second example, which will be analyzing the quantum yield of cis to trans photoisomerization process of azobenzene. The reference for that is provided here. This is figure 7 and the text of the paper. So to do that, we will first need to define a list for the dihedral angles of azobenzene, and then we'll iterate over the 50 trajectories provided in the data, again loading each one of them and taking the final geometry in each of the trajectories and extracting the dihedral angle and appending to this list. So here we should notice that the geometries, that the trajectories are provided in a slightly different format, with each trajectory being in a separate catalog. However, this is the typical output of the mlatoms.simulations that run in parallel functionality, which is the recommended one to run multiple trajectories in parallel. Okay, so the results have loaded, and here we can just look at one representative trajectory using the functionality trajectory.view. And here we can see how the trajectory plays out and the photoisomerization process occurs. And the next step would be to plot a histogram of these dihedral angles. Again, we use matplotlib for that. And if we look at the histogram, we can see that it has two maxima with respect to the dihedral angles. One for smaller values of dihedral angles, and this corresponds to the cis isomer, and one for bigger values of the dihedral angle centered around 150-140 degrees, and that is the trans isomer of the diazobenzene. So to obtain the quantum yield, we need to calculate the fraction of trajectories that relax to the trans isomer of azobenzene. To do that, we iterate over the list of the final dihedral angles and count the number of dihedral angles that are greater than 60 degrees, taking that as a descriptor of trans azobenzene. We do that, and finally we can print out the quantum yield as our count divided by 50, which is the number of trajectories, and multiply by 100 to obtain the final quantity in percent. And we obtained that the final quantum yield is 68%, which, by the way, agrees very well with experimental data. And okay, that is everything that I would like to show you in this tutorial. If you have any problems or questions regarding mlatom, then do not hesitate to contact us, preferably via the Zax support Slack.